Welcome to section 11.3. This is going to extend our knowledge of probability a little bit farther by having us look at something called conditional probability and then also what they're calling and probability as well. And so we'll look at this together. Again, you have the instructional aids that are provided to you through my math lab, and so hopefully those are going well. They should have video lectures and videos of them working sample problems, but I just wanted to do some together with you myself, and then you could hear my perspective as well. Conditional probability is what I decided to type out first, and it is really the first thing that they handle in this section. This is also sometimes called given probability. So what happens in this situation is we know something. So the given really means we know something about the situation. So typically we're not looking at the entire population. So an example of conditional probability would be something like this. Find the probability that a randomly selected student from our class has brown eyes given that they are female. And so it's that last part that puts a condition on it. So remember I said given that they are female. So apologize, that's my hand going crazy there. Probability that they had brown eyes given they were female. If I were talking about our class as a whole, the denominator would be 25 because it would be 25 ways to pick a person from our class. But because I know that the person has to be a female, I'm given that. Whatever you're given is the bottom number would be the number of female students. And the top number would be the number of brown-eyed female students, right? I wouldn't look to any of the males because I know that the student is a female. So whatever you're given is what you know. So I looked in the book and I found this example right here that I thought was understandable enough for us to have an example given to you of conditional probability that I don't think will get away from us. So we have a sample space that consists of all the numbers between 1 and 15, all the whole numbers. So 1, 2, 3, 4, all the way up to 15. And we're going to just draw a single number from that. And the events that we're going to talk about is the event A will be the numbers even, the event B would be the number is a multiple of 4, and the event C would be the selected number is a prime number. So, and then it will say find the following. So previous to this section, we could do something like this. A. Just find the probability of A. That's from 11.1. And we would say, okay, that's the probability that the selected number is even. So what would we do? We would say, well, we have 15 numbers, and the even ones are, and we count them 2, 4, 6, 8, 10, 12, 14. And there would be 7 numbers, right? 7 numbers that are even. And there we go. It could be from 11.2 and have the probability of something like not A. We know the probability of it not being even is 1 minus 7/15 from what we did last section for 8/15. Or equivalently, there's 8 non-even numbers out of 15, or in this case, 8 odd numbers out of 15. It could also be from 11.2 where we had something like this, the probability of A or B. They may mix the sections in. I didn't want that to confuse you. It's actually really good. It'll help you prepare for the test. Well, this means the probability of A, that's the probability of the numbers even. We've already done that, 7/15. Remember the formula, probability of A, plus the probability of B. What's B? B is that it's a multiple of 4. So what are the multiples of 4? 4, 8, and 16. Well, that's 3 numbers out of 15. Ooh, I said something, right? I said 4, 8, 16. But I shouldn't. I should have said 4, 8, 12, 16. And the 16 we're not counting, but I'm still right. 3 out of the three numbers in that block are multiples of 4. And so let me just get rid of that 16 in there and just 4, 8, and 12. And now we need to say, are they mutually exclusive? Because if they're not mutually exclusive, I have to subtract out the A and the B. So remember what A was. A was even. Are there any multiples of 4 that are also even? If so, I've double counted them, and yeah, all 3 are. So I would take out all 3, and we'd be left with this 7/15 probability. Essentially, they're kind of wrapped up into to be the same number. So not the greatest example, but it does happen that way sometimes. If you're okay, I'm going to erase this. You can always pause the video, but I don't want to get too low. Let me show you a question from this 11.3 section. It's going to have some symbology that's in there, some symbols that I want you to understand in case you see them in the homework or on the exam. They're going to have something that looks like this for 11. I'll keep the same style, 11.3 problem. Find the probability of A given B. All right. I am hesitating for just a minute and wondering if this is a good first example, but it is what it is. So the probability that it's A given that it's B. So this slash mark here means given. We absolutely know B has happened. B has occurred. So what is B? Multiples of 4. Let's remind ourselves about those. 4, 8, and 12. And so the question is, what's the probability that A happens given that B has already occurred? So knowing that we have a multiple of 4, what's the probability that the number we select from these 3, so my base number is 3, is even? Well, the number of even numbers in there is 3, and so therefore it's a 1. It's sure to happen. And so that's what given probability or conditional probability is like. What about something like this? A given C. Now C is a prime number. I don't know if you remember prime numbers. We will look at them in our class at some point. I think at the very end. 2 is the first prime number. A prime number can't be broken down to anything other than 1 times itself. So 2's like that. 1's not considered prime at all, nor is it considered composite. It messes things up, so we just leave it off to the side. 3 is prime. 4 is not prime though, because it can be broken down to 2 times 2. 5's prime, but not 6. 7's prime, but not 8, because 8 is 2 times 4. 9, no, because 9 can be 3 times 3. 10, no, 2 times 5. 11, yes. No other breakdown than 11 and 1. 12, no, 2 times 6. 13, yes, because it's only 13 and 1. 14, no, 2 times 7. 15, no, 3 times 5. So these are our prime numbers. So we are given that C has happened, or is a condition on it. I'm sorry, the condition's been pulled out. So we pulled out all the prime numbers, and the question is, what's the probability of randomly selecting an even number from this list? Well, how many are in this list? 1, 2, 3, 4, 5, 6 are in that list, only one of which is even, and so we get a nice 1/6 out of there. And you'll get lots of practice with that in the homework. The other thing that's being taught in this section is the probability that of A and B. That's the way they refer to it, but what that means is the probability that A happens and then B happens. And so there is a formula for that. I don't think I can write it in between here, so I'll put it off to the side over here. It is the probability that A happens and then multiply by the probability that B happens given A that has already happened. So we want to make sure that we know A has happened before that second thing happens. And this would extend to the second, third, fourth, fifth thing as we go forward. So if there were 5 things, it would be the probability A happens, probability B given A, then given both of those have happened, what's the probability of the next? And it's way easier to just think about and do than it is to write in some kind of formulaic way. So they usually don't. They usually just stop just like this. So in the book is a question about a shelter, a non-kill shelter, a no-kill shelter, that has 7 puppies, including 4 huskies, 2 terriers, and 1 retriever. And so this is the typical style of question that's in here. If Rebecca and Aaron both select one puppy at random with replacement, so what that means is Rebecca's going to go in and choose an animal, right, a dog, and then they're not going to say, she's going to say, I like that one, but they're not going to remove the dog. Aaron's going to come in and have the same look at all the animals that are there and be able to choose any one of them, including the one that Rebecca has already chosen. So we want to find the probability of each event. Find the probability that they both, and I just want to make sure that I'm wording it the way they do. Yeah, they both select a husky. Okay. Well, you handle it one at a time. So what this means is there's 2 selections. There's Rebecca going in to make her selection, and then Aaron's going to go in and make his selection. So Rebecca goes in first, and how many dogs does she see? She sees 7 puppies, of which how many meet her condition of being a husky? She has 4 ways out of 7 to pick that, and she does. She chooses one of those. Then Aaron comes in, and Aaron, because we did not remove the dog, Aaron's looking at 7 dogs, 4 of which are terriers. So it's very common for these to be the same number when the events are independent, when it didn't really matter what Rebecca did. So it didn't matter what Rebecca's choice was because it didn't remove a choice for Aaron. And so we're almost done. We have 16 over 49 as our answer, and that doesn't reduce at all. They could ask this, the probability that Rebecca selects a terrier, and Aaron selects a husky. And they'll just mix and match these. And so we deal with the first person. So that's the intent of the formula. Hey, just deal with one thing at a time. Let's let Rebecca go in and get her terrier. How many animals is she looking at? 7. How many are terriers? 2. And then again, we're not removing them. We're replacing that dog. So maybe she picks up the dog and says, I want this terrier. And they say, great, and they put it back. And then Aaron walks in and he's still seeing 7 dogs. And how many are huskies? 4 of those 7 dogs are huskies. And so now we get 8 over 49, and we're moving on. So the other thing that they could do is, and it's in the next block of problems, is they say without replacement. So this is the situation that's more normal. Let me write that a little bit better. It's more normal for events to happen without replacement. So it's more normal for Aaron and Rebecca to talk and allow one of them to choose first. So maybe they talk and they say, hey, Rebecca, why don't you choose first and I'll take what's left. So if we answer the same questions without replacement, meaning the probability that they both select a husky, so this definitely means that they can't select the same one. So they walk in and Rebecca goes and she selects a husky. What's the probability of that happening? Well, there's 7 dogs present, 4 of which are huskies. And now we're going to get to, and I'll highlight it, this part of the, it's not highlighting. Let me grab the highlighter. We're getting to this part of the formula here. And not sure why that ruler came up, but it's here and now it's gone, so that's awesome. So the probability that they both select a husky, Rebecca walks in, 7 dogs, 4, and she chooses one. Now when Erin walks in, how many dogs are there? Well, given that she's already selected a dog, right? There's only 6 dogs remaining because that dog was removed. And how many of them are huskies? 3. And so we get a different probability. We get, well, let me reduce this. 1, 2. We get a nice 4 over 14, which can still be reduced to 2 sevenths, right? Sorry, I didn't see that earlier. We get 2 sevenths instead of 16/49 out of that. Then the probability that Rebecca gets a terrier, and then Erin comes and gets this husky. Well, let's let Rebecca go in and get her terrier. When she goes in, there's 7 dogs present, 2 of which are terriers. Now there's only 6 dogs remaining for Erin. How many are huskies? 4 of them are huskies. And so we can simply do 1, 3, and get 4 over 21 as our probability. This is an example of a non-independent setting where it makes a difference what happened in the first pick for the second. So you'll see the definition being asked about of independence. They'll ask, hey, are these two events independent? They are independent if one doesn't affect the other. So without replacement, they were completely independent. Didn't matter what Rebecca picked because it didn't affect Aaron's ability to pick the dog that he wanted. However, in the second situation, it does affect Aaron because he has less of a choice either way, whether they're both doing the same thing or it's this terrier husky thing. So I think this video will help to augment what you're already having. Thanks so much. Have a good day.